Hello, everyone. Thanks for joining us. Welcome to the 76th online Spintronics seminar. This week, we have Professor Sunxiang Huang as our speaker. He received his PhD in physics at the Johns Hopkins University in 2011. He joined the Department of Physics as an assistant professor at the University of Miami in 2014. His research interests lie in novel quantum spintronic materials, which bridge emerging fundamental physics and technological applications. His recent research focuses on the epitaxial thin films and heterostructures of topological Kagome metals, and the studies of their topological, spintronic, and superconducting properties. So without further ado, Professor Huang, please go ahead with your talk.
Thank you for the introduction. It's my great pleasure to present our work on the epitaxial thin films of the topological Kagome metals. I will start with the brief introduction to the topological Kagome metals, which we call the TKMs, and discuss why they are interesting in many aspects. Then I will describe our efforts to realize the high-quality epitaxial thin films and the observation of many unusual physics in those films, such as the Kondo effect and possible superconducting triplet pairing in these heterostructures. So when I knew the Kagome was many years ago, I thought it was a name from some famous people. So if you Google Kagome, in fact, the first result you got is a name from Japanese fictional character. So fortunately, the Kagome we discussed today is still ranked in top 3 from the searching result. So the Kagome means it's a bamboo basket woven pattern. It's a Japanese compound words that include cargo, which means basket, and mu, means eye and hole. In Chinese, it reads long and mu. So the Kagome lattice resemble this pattern that have these so-called corner shaded triangles. So each lattice point has 4 nearest neighbors. So in the spin systems, this triangle geometry could induce geometric frustration. For example, in these antiferromagnetic coupling systems, these 2 spins are aligned in antiparallel. So the third spin in this corner is frustrated because it doesn't know which orientation it should stay, because for either this up or down, the system has the same energy. So in many of these Kagome magnets, there are spin glass state and the possible quantum spin liquid states. More interestingly, just like the honeycomb structure of graphene, so this simple 2-dimensional Kagome lattice plus the tiny binding give rise to the exotic band structure with coexistence of the Dirac fermions as well as the flat band. So probably all you have heard a lot about the Dirac fermions, which will induce many interesting physics, but same as the Dirac fermions, the flat band also give rise to many interesting physics. The flat band is highly degenerate and could be dispersionless. Is a counterpart of the Landau level at a 0 field. So therefore, we could realize fractional quantum Hall effect at a high temperature without a magnetic field. So these highly degenerate electrons may induce unconventional ferromagnetism or superconductivity, as observed recently in twisted bilayer or trilayer graphenes. In addition, on the materials wise, the Kagome lattice are often occupied by 3D or 4F elements, which usually have rich magnetism and strong electron corrections. So these topological metals, which have this two-dimensional lattice structure and host Dirac Weyl fermions and flat bands, provide an exciting platform to study the new topological physics. So the TKMs have different compounds, like for example, the binary and trinary compounds. So in the case of binary compounds I will discuss, it has this T3X Kagome layer. So the T represents the transition metals, the X could be the germanium, tin, or indium. So the transition metal form this Kagome lattice, but in the center of the hexagon, there is X atoms. So with these T3X layers, we can stack them in different way. So we can stack them in like this 3-1, 3-2, and a 1-1 like composition. So for the 3-1 case, the Kagome layers are stacked together with in-plane offset. So we have the stacking like a BA, BA, BA. For the 3-2, the stacking is much more complicated. So the Kagome layers are first stacked in this bilayer structure, but the stacking is different. So we have this AC, this could be CB, this is like BA. In between the bilayer Kagome lattice, there is this X layers with honeycomb structures. So these 3-2 structures. For the 1-1 structures, these Kagome layers are stacked with single layer separation of these X layers. So they have the stacking like A, X, and A. So from 3-1 to 1-1, the separation between the Kagome layers increases. So the 1-1 materials is closer to the two-dimensional limit. We may also insert more like atoms for the separation in the case of the cobalt-3, tin-2, sulfide-2. So that in addition to the separation of the tin, there is additional separation of the sulfide layer. It's probably because of the relatively large separation between them, many also unusual physics as have been observed in these compounds. So for the trinary compounds, there are like 1/6 structures which are often ferrimagnets. In the case of this compound, the moment is aligned along a C-axis, which later induce this gap at the Dirac fermions and many interesting physics. For the 136 cases, right now it's some the superconductivity has been observed in those compounds, and they show some unconventional behaviors. So in this talk, I focus on the binary compounds, the ferromagnetic white metal, Iron-3-tin-2, antiferromagnetic white metal, Manganese-tin-1, and the antiferromagnetic Dirac metal, Iron-tin, as well as the paramagnetic Dirac metal, cobalt-tin. Okay, so I will first briefly discuss the interesting property observed in bulk materials. Let's start with the Manganese-tin. So it is antiferromagnet with near temperature about 420 Kelvin. So each manganese carry moment about 3 μb. They have very rich non-collinear spin texture, roughly between like the near temperature and some transition temperature T1. we have the so-called inverted triangular spin texture. Below T1, we have this modulate or this kind of spin helical state. In some cases, there could be another transition below this transition temperature, the spin gas state. So the T1 and the TG depend sensitively on the composition and the fabrication process. So it is an antiferromagnet. So usually the net moment is close to 0. So that's also the case for this. So despite that, the manganese has large moment of 3 mu B, they have this nearly perfect triangular orientation configuration. So the net moment is close to 0, but still carry, there's a little bit tilting. So there still has very small like net moment. If we apply the in-plane field in the Kagome plane, this net moment can be switched. The direction can be switched, meaning this kind of polarity is reversed. So it shows in the magnetic measurement here when the field is along the Kagome plane. So for common antiferromagnets, because of the nearly 0 moment, the normal Hall is close to 0. It's usually like 0. However, in these materials, there is a large normal Hall effect if the field is in the Kagome plane. So this unusual normal Hall likely originated from the Weyl nodes near the Fermi energy. So this is the serial calculation shows there are 6 pairs of the Weyl nodes which are observed by the photo emission experiment. So there are also many other interesting spintronic properties in this system, such as the magnetic spin Hall and the inverse spin Hall effect. So the best idea is the spin current generated by the Manganese-tin depends on the chirality of this triangular spin structure. So we'll come back to this later for a little more details. Now let's move on to the next materials, for the magnetic wire metal Iron-cobalt-tin. It is for the magnetic materials with Curie temperature about 670 K. It's really high, so that's good for application. For the bulk single crystals, the magnetic axis rotated from CS at a low temperature towards to the epiplane at a low temperature. Interestingly, if we apply the magnetic field along the C-axis, we can observe rich spin textures, such as the magnetic skirming as observed by the Lorentz TM measurement. So this is like the real space spin textures in this compound. As mentioned, this Kagome lattice give rise to massless Dirac fermions. If the time reversal symmetry is broken by this ferromagnetism, the spin degenerate Dirac bands is lifted. Inclusion of the spin orbital coupling opened the Dirac gap. So this is the idea about the band structure. So experimentally, did the photo emission measurement, indeed observe this Dirac gap about 30 milli eV below, which is about 70 milli eV below the Fermi energy. That's another one here. So in this paper, suggest the large anisotropic normal Hall observed in these materials arising from this massive Dirac gap. So here shows the normal Hall conductivity in these materials. For the field along the C-axis, the A normal Hall conductivity is relatively large and increase low temperature. But for the field in the AB plane, the normal Hall is much smaller. So the comment from some theory and suggests the observed intrinsic normal Hall comes from this Dirac gap, and the value depends on the gap value. But there are also some other results suggest in this material there are also Weyl fermions very close to the Fermi energy. So in this work, they did some DFT calculation and the upper measurement. So they suggest very close to the Fermi energy, there are something Weyl fermions which can be like whose configuration can be tuned by the direction of the magnetism. So this scenario is further supported by the optical measurement on these materials. So the optical conductivity measurement shows the contribution from the Dirac bands as well as the flat band. It's interesting that shows the flat band, the flat band is very close to the Fermi energy. It's only about 10 to 20 milli eV. So further analysis indicate this sharp peak depends on the temperature. This dependence happens coexistence with the spin orientation, which happens about 150K at the bulk single crystals. So the attribute this sharp peak to the Y nodes near the Fermi energy, which can be sort of switched by the spin reorientation. Lateral flat band has also been confirmed by the STM measurement. Although the flat band is about 200 milli eV below the Fermi energy. Another interesting property in this material is done by the quasi-particle interference measurement using the STM. So the basic idea is the aforementioned Dirac gap can also be tuned by the orientation of the magnetization. So this shows with the magnetization along different directions, this quasi-particle interference pattern is different, indicating the gap value is different. So let's, in short, these materials, just like the manganese-tin, is another exciting materials we should explore. So let me quickly go through the antiferromagnetic Dirac metal Iron-tin. So it's an antiferromagnet with near temperature about 370K, but it's a collinear antiferromagnet. So in each Kagome plane, the spins are along like one directions. Between in the neighboring Kagome planes, the moment are aligned independently. So the photo emission measurement also confirms the Dirac nodes as well as the flat band in these materials. Also, another interesting feature for this is also kind of special antiferromagnet with PT symmetry. So now let's quickly go through its sister compound, the paramagnetic Dirac metal cobalt-tin. So in this compound, one interesting feature is that the band structure depends on the orbitals. So in other words, different d orbitals give rise quite different the band structure. Interestingly, so the flat band in these materials is rather flat and broader in momentums. there are a couple of flat bands as well as the Dirac points shown here. Because of this, so loss general feature have also been confirmed by the photo emission measurement. So because of loss flat band, the density of state shows a large peak below the Fermi energy. Because the iron-tin and the cobalt-tin are isostructure, so they can be doped to each other. So later we can get like this compound iron-cobalt-tin with composition with X value from 0 to 1. So for the X equals 0, we have the iron-tin with the planar antiferromagnetic alignment. The moment aligns in the Kagome plane. By replacing about 20% of iron with cobalt, we have this spin reorientation. So the moment actually turns to auto plane along the C-axis. So also from this paper also shows some following work, shows that probably are some spin gas along this region. So anyway, so that's another kind of special feature for these 1-1 systems. So hopefully I have convinced you that all these 4 materials are very interesting, and but most of the work on those materials focus on bulk materials. With these special materials, so they have the special symmetry and have the interaction between like topology, correlation from like D or F electrons, as well as the magnetism. So these features make these TKMs excellent platform to study new topological properties, such as loss in the topological spintronics, topological superconductivity, flat band physics, and maybe new topological, new correlated topological phases. So most of the work so far focus on bulk materials. So I will discuss in the following. I will discuss our efforts to realize the high quality films and the observation of many unusual features such as the Kondo gap opening in the Manganese-tin and the possible superconducting like triplet pairing in the heterostructure. So for those binary compounds, they have the hexagonal structures with a lattice constant A more than 5 angstroms. The lattice constant of like common hexagonal substrate aluminum oxide has lattice constant of 4.76 angstrom, which is about is more than 10% less than those values. However, if we rotate this aluminum oxide 0.1 by 30 degrees, we can actually get a good lattice lattice match between the aluminum oxide and the platinum 111. If we look at this value, this is 4.81 and this is 4.76. The difference is less than 1%. And now if we look at the least length, it's about 5.55 angstrom, so which is about like a 2% difference with the Manganese-tin. So furthermore, this lattice mismatch, the lattice mismatch between the platinum and the lutetium is also about like a 2% range. So we could also grow like lutetium on top of platinum, and for this lattice constant is also within about a 2% difference with the lattice constant of these 3 materials. So in other words, we may be able to grow epitaxial these TKM films by using the platinum or lutetium buffer layer on this chip sapphire substrate. So we have managed to grow the high quality epitaxial films for all these 4 materials mentioned. The 2 theta omega scan in the first scan shows a strong diffraction peak without the noticeable impurity peak. In addition, we see the lower oscillation along the main peak. This indicates the sharp crystalline interface in the films. The locking curve, the omega scan with the triple axis analyzer shows the peak is extremely narrow with the width around the like 0.002 degree, which is the limit roughly close to the instrument limit. So this indicates we have actually the Kagome plane is perfectly parallel with the film plane. The implant FeSn also is also very narrow, which indicates the implant alignment between different grains are almost perfect. The reflectivity measurement shows this oscillation peaks from low angle to about 10 degrees. So this shows the films has sharp interfaces and a smooth surface. So we did we also make some this Huang or Manganese-tin films as shown here. So this also the XRD shows only the like 1 to 2 peaks without the other orientations. To further confirm the crystalline quality, we did the TM measurement. So here shows these films has quite well layered structures. The interface roughness and the surface roughness is roughly less than 1 nanometer. The high magnification scanning TM image shows the desired atomic arrangement with low crystalline disorder. As discussed earlier, to grow epitaxial TKM film on this substrate, we need this sort of 30-degree orientation for the aluminum oxide 001. So this is confirmed by the implant FeSn for the substrate as well as the buffer and the films. So clearly, the 30-degree offset is observed in this FeSn. Now, with those films, so thin film, the epitaxial thin film is not just like the same counterpart of the bulk materials. Because of the non-equivalent nature of the fabrication process, we can actually get much more than just the same counterpart of the bulk materials. So as shown here, if we write the composition of the Manganese-tin film in this formula, so the X represent like how many tin atoms are replaced by the manganese atoms. So we can, in the same film, actually we can get the X up to around 0.55 without introducing impurity phases. So this is much larger than later reported in the bulk materials, in which the X is only about 0.15. So in other words, we have greatly extended the compositional range that the bulk materials doesn't have. So roughly half of the tin atoms can be replaced by the manganese, let's say manganese impurity. So what's the new physics we may get from this extended doping? So before I discuss the transport property, let me briefly discuss the classical correlation effect, which is the Kondo effect. The Kondo effect was observed experimentally almost 100 years ago. So for usual metal, when we decrease the temperature, the resistance will decreases and reach some residue value due to the impurity scattering. But for some materials systems, so people observed the resistance reach to some minimum value at a certain temperature, after that, the resistance actually increases. So that troubles physicists for many years, for about like 30 years, until Kondo gives an explanation. So the basic idea is, so in those systems, there are magnetic impurities. So the spin exchange scattering between the conducting electrons and the localized moment gives rise to this sort of additional resistance. At the zero temperature limit, the conduction electrons and the localized moment form this so-called Kondo singlet, and the localized moment is screened in the zero temperature limit. When this magnetic impurity forms like a lattice structures, the Kondo effect develop coherence and eventually develop a hybridization energy gap. So this we call the Kondo insulator. So inclusion of this topology in the Kondo insulators give rise to the topological Kondo insulators, such as this SMB6 with the surface conducting channel that give rise to the resistance plateau at the room temperature. Okay, so now let's look at what happens when we have the extended magnetic doping in these same films. So from the low doping to the high doping, the resistance versus temperature curve shows different behaviors. For low doping, it has the metallic behavior with some residue resistance. For the high doping, we actually see sort of like a semiconducting or insulating behaviors. So if we zoom in for this x equal to 0.27, we see the resistance minimum around 25 Kelvin. By careful analysis, we can get the Kondo temperature is about 8.5 Kelvin. Further increase the doping increases the Kondo temperature at the high doping range. We see this like insulating behavior. By careful analysis, we obtain a Kondo gap value about 10 meter eV. So we also did a terahertz transmission measurement showing here. So this is a transmission curve for the films with these two competition. So clearly for the highly doped one, there is a prominent dips corresponding to this energy gap around at about 1.3 terahertz, corresponding to the energy of about 5.5 millieV. Now, well, we see the Kondo like a coherent develop in this system. What other effect we may observe? So we first did a DC Hall measurement for different doping samples. For the low doping one, we observed the large normal Hall effect at loss in the bulk samples. So this normal Hall decreases as the temperature decreases. For the highly doped one, the negative abnormal Hall, the value is much smaller than this low doped one. And the abnormal Hall even changes sign at around like 200K. So why we have something like this? So we also did this terahertz Hall effect measurement. That is the terahertz Faraday rotation. So the idea is the polarization of light will the angle the polarization will like tilt the angle when the polarized light passes through some magnetic materials. So this is basically measure the terahertz Hall effect. So if we look at a low doped one, the this Faraday rotation, so the Faraday rotation are real part and the imaginary part. So for the lower dopant one, this Faraday rotation is very small and weakly depends on the magnetic field. However, for this Kondo Kondo insulator state, we see we observe the resonance enhanced Faraday rotation. So the signal is much larger than loss in the lightly doped sample, and it depends on the frequency. The resonance happened around 1.3 Tesla, corresponding to the energy gap of 5.5 millieV. So that may indicate for the highly doped sample, we may have some new topological state, which could be a magnetic topological Kondo insulator. Now we look a little more detail about the DC Hall effect as a function of temperature for different composition. So for the low doped sample, we have large negative normal Hall at room temperature. It decreases, and it seems that there is a phase transition around 225 Kelvin. Below that temperature, this normal Hall decreases slightly as temperature decreases. For the highly doped one, the normal Hall, the negative normal Hall is much smaller. It's roughly 1 order smaller than this highly doped one. And it changes sign along this temperature. Below that, we have the positive normal Hall, which increases with temperature. So if we summarize this figure in this contour map, so the color represents the normal Hall resistivity, and the y-axis is the temperature, the x-axis is the composition. So we can see the y-semi state probably happens along this range, this composition, as well as the temperature range here. So below this temperature, we may have this spiral structure or possibly spin glass state. In this range, we have this Kondo gap state. This is the result for the 110 films. The Kondo physics is similar for the 110 and 01 films, but for the normal Hall effect, the 01 film shows quite different behaviors. So the 1 Tesla loop shows 1 Tesla loop or the Hall resistance shows no hysteresis and 0 remnants. But the 9 Tesla loop shows clear hysteresis and finite remnants. If we subtract the linear background, we get it's a normal Hall contribution. So this is likely due to the spin chirality in real space. So the idea is because of this triangular spin structure or this heterostructure, if we apply the field perpendicular to the plane, the moment will be tilted slightly out of plane. So if with this tilting, we get a finite spin chirality, which induce topological Hall, just like the topological Hall observed in the skirming phase. With the extended magnetic doping, so let the magnetic impurity like manganese, for loss of manganese, the spin are likely to be randomly oriented. So that sort of give rise some positive and some negative spin chirality and reduce this spin chirality. So that's what we observed here. Okay, so now let's move on to what the interesting feature. Oh, so I probably run out of time. So let me maybe quickly go through that. I like to discuss the superconducting for symmetry effect. So anyway, so let on the 3-2 films, the one feature is in the same films with this in plane anisotropy. So actually, we the moment it tends to rise in plane. So actually, that's probably good for the this wire nodes physics as observed in this optical measurement. And we also did a anomalous measurement which measures the Barry curvature near the Fermi energy. So those shows the samples has large anomalous nonce, which may be also arising from the wire nodes near the Fermi energy. Okay, so for the anti-Fermi one, let's we can confirm there's anti-ferromagnetic, and there is also large steeping training effect or the exchange bias indicate that in the same frame there are multiple equivalent magnetic ECSs. Now let's, okay. So that maybe this may be a lot, probably most audience are interested in this, but let me quickly go through this. Because of the special like magnetic symmetry in these TKMs, so one application in the spintronics is that if we apply charge current, we may realize the spin current with the spin polarization along X or Z direction, in addition to the common like Y direction by the spin Hall effect. So this has been demonstrated recently by the switching experiment in the Manganese-tin nickel cobalt with perpendicular magnetic anisotropy. So the basic idea is with this spin structure, there is a Z spin polarization that gives switching without the bias field. So we also have observed many interesting features in this matter. Unfortunately, I'm in collaboration with Professor Shaw, but unfortunately, I don't have much to discuss today. But another thing I like to discuss is recently we observed some very interesting second harmonic Hall in this iron-tin films, which is antiferromagnetic. So we, by applying current with density around 7 to 10 to 9 ampere per meter square, we observe a relatively large second harmonic Hall signal, which depends on the magnetic field. So we are not sure what that come from. It's come from a spin torque or like a magneton scattering or some nonlinear Hall due to the wide fermions. So we still don't know yet, but it seems it's a very interesting topic to move forward. Okay, now let me go to the last topic. I'm trying to wrap up quickly. Because of the rich spin texture in the TKMs, the spin texture could be the real space spin texture like spin helix or skirming. It also could be the spin texture in the momentum space due to the like Dirac fermion, wide fermion, etc. So when these spin texture interact with the Cooper pair, the Cooper pair may experience spin mixing and spin rotation. So in other words, for the singlet Cooper pair, interacting with the magnetic inhomogeneity, that could be in the momentum space too, we can get the superconducting triplet pairing, which has a very long decay length. So that for triplet superconducting, normally are topological and also are very probably a very interesting application in the superconducting spintronics. So for the Manganese-tin film, as I discussed, I have rich spins, non-collinear spin structures in real space, as well as probably different topological phases. So let those features make us the Manganese-tin an excellent platform to study possible topological superconductivity in these systems. So very recently, Parkins group fabricated the lateral Josephson junction, which are made of the manganese-3 germanium and the niobium leads. The major Josephson critical current for like a different device with different separation between leads. So the main result that got is that this critical current, Joseph current, decays slowly with the separation between the superconducting leads. So the come out of a model and suggest the decay length is like about 160 nanometer. That is much larger than the superconducting coherent length of niobium, which is about 10 nanometer in thin films. So we also work on this matter like about years ago. So we made the Manganese-tin niobium heterostructures shown here. So the in-plane 5 scan shows the niobium glow quasi-epitaxially on the Manganese-tin with the relatively broad peak. So one characteristic feature of the proximity effect is the suppression of the superconducting transition. So we also made this control sample, and we first look at the superconducting transition for the, we call it the single layer and the bilayer structures. So clearly, the bilayer has lower transition temperature than that of the single layer with the same thickness. And the difference increases as the niobium thickness decreases. Interestingly, we also observe this step-like feature in the bilayer. So we are not quite sure what the reason yet, but this feature is also has also been observed in the heterostructure between niobium and ferromagnetic helical magnets, such as this ER. One reason it could be there's some magnetically inactive region, so that there is no proximity effect. But another possible reason is the interaction between the Cooper pair and these helical spin structures. So that's we don't have a definite answer yet, but I think the second scenario is very likely because we have another sample like shows no this transition anyway. So if we plot the TC as function of the thickness for a single layer, the niobium, the TC of niobium inversely proportional to the thickness. But for the bilayers, the dependency is like the thickness to -1.5 power. So this result here shows the very strong proximity effect in these systems. So to study the possible triplet pairing in these systems, we did the RT measurement at different in-plane and out-plane field. From these RT curves at different field, we can obtain the upper critical field and the corresponding transition temperature. So we plot the out-plane critical field as function of the temperature. So it shows for the out-plane field, the critical field linearly scale with the critical temperature. For the in-plane field, the critical field square linearly scaled with the transition temperature for the transition temperature roughly about 75% of the transition temperature at zero field. So this feature can be well described by the two-dimensional Ginsburg-Landau series, showing in by these two equations. So by getting the slope and the intercept of these dashed lines, we can get the critical field at a zero temperature and the critical temperature at a zero field, as well as the Ginsburg-Landau coherent length. So we plot those coherent lengths as a function of the niobium thickness. So for a single layer now being the coherence slightly decreases as the thickness decreases. However, for the bilayer, the coherence increases. For the 50 nanometer samples, the coherence increases by about 50%. So this may be an indication of triplet pairing. Another important quantity in superconducting is this is the ratio between the critical field, upper critical field, the impedance upper critical field at 0 temperature to the critical temperature at 0 field. So there is important quantity, this is called a polyparamagnetic limit. The basic idea is if we apply large magnetic field, the sigma energy will overcome the superconducting pairing energy. So that superconducting gap gives an upper limit of this ratio. For a singlet, without a coupling, without spell coupling, the limit is about 1.84. So in the films, for the 50 nanometer one, we got the value is about 1.9, which is slightly above the limit, although it's still kind of within the experimental uncertainty. But nevertheless, so this result indicate the triplet pairing may be plausible scenarios for the in this system. Okay, so to summarize, I'm out of time. So to summarize, we have realized the high quality epitaxial films of various TKMs. With those films, we observed many unusual physics, such as the Kondo gap opening and the potential triplet pairing and heterostructure. So this work could not be done without the hard work from my graduate students, as well as the generous help from the collaborators. Thank you for your attention.
Thank you very much for this interesting talk. Let's use the reactions button to thank the speaker. So this talk is open for questions. If you have any question on Zoom, please use the raise hand function of the button. You can find that also on the reactions. And if you're watching this on Twitch, please just type your questions in the chat box. Okay. Do we have questions? See one, Kirill, please go ahead with your question.
Yes, thank you for the interesting talk. So I was wondering if you could say what you think about the way we should think about the Kondo effect in an antiferromagnet, right? So usually we think about, singlet state of the conduction electrons and the localized spin, but if the spin is in the antiferromagnet, so does this mean there should be some fraction of spins that are essentially not coupled with the rest, like loose spins, or what is it?
Yeah. So because so in this system, I think the coupling is between the conducting electron and this so-called impurity manganese atom. So those atoms is likely replace the tin here. So the interaction is likely happens between the conducting electron and the manganese atoms occupied on the tin side. So
and they have zero coupling by symmetry to the.
You mean the coupling for the manganese between this manganese and the other manganese?
Mm-hmm.
Yes. That's a good question. We actually don't know, because if we look at the symmetry, it seems that should also may have some coupling between them. But
well, I mean, in the Heisenberg model, it looks like it will add up to zero, but there may be higher order interactions as well. Mm-hmm. And how sensitive is this to those couplings? I mean, how much interaction would destroy the Kondo state? I mean, it's just a few Kelvin, right? So it looks like you don't have a lot. Are there some estimates as to?
Yeah, probably not. Yeah, because the less energy, the gap, even in the highly doped one, is about 10 meter eV, which I think is much smaller than the extrinsic coupling.
Yeah. Okay. Thank you.
Okay, I'm going to read a question from Praja Laxmisha. Is there a disadvantage in using buffer layer to grow these films as opposed to not using them at all in terms of the spin orbit torque measurement?
Yes, I think that is a disadvantage because in these systems, the materials we grow for the magnetic-tin, we need a platinum. So that platinum is for the spintronics. I mean, in some sense, it's good materials, but in some sense, it's a better material. So that's actually for this aspect, it's we don't want to have like contribution from like the platinum. Right? But so the measurement we are doing is we try to grow the magnetic-tin a little bit thicker. So according to some early result, the spin difference in magnetic-tin is very small. It's only like 1 nanometer or 2 nanometer. So in that sense, if we have, let's say, magnetic-tin is like a 10 nanometer or more, so the contribution from the platinum, the contribution of the spin current from the platinum probably is not an issue. Yeah, but overall, in some cases, we do want to have the film, not just the magnetic-tin, also the other films, which can grow directly on insulating substrate. So we can really, especially when we make the films very thin, so we may really see some this quantum confinement effect without the sort of the contribution from like a trivial like a buffer layer, the trivial contribution from buffer layer.
Thank you very much. Do you have any other question? Weyl, please go ahead with your question.
Sunxiang, thanks very much for the very nice talk. Can you talk a little bit about this harmonic Hall effect? So what are you actually measuring? It seems like you need a lock-in amplifier. Maybe?
Yeah, we use lock-in and we pattern the sample into the Hall geometry, and we apply the implant field, just like the spin orbit torque measurement in those material. But this result comes from the Iron-tin layer without the magnetic layer. So this is we use lock-in. Yeah.
So this is just a second harmonic signal from the anomalous Hall voltage.
From the multiplied is the planar Hall. It's in the planar Hall geometry. So the field is in the plane.
Oh, okay, I see. That's why you have angular dependence.
Yeah, but this look like if you do the second harmonic on let's say platinum cobalt platinum permanent, so you also see something later. But for this sample, we don't have additional ferromagnetic layer. So that's
okay.
Yeah.
So basically, the Iron-tin itself give you a signal almost like a bilayer.
Although that also has like a CD layer, like platinum ruthenium, but yeah, so we don't know what it is. Like could be due to the magnon scattering, probably likely a scenario. Yeah, but that's kind of the large signal because we measure other these bilayers even with the ferromagnetic layer. So in some cases we couldn't even get this signal.
Okay, thank you.
Sure.
Is there any other question? me check on Twitch. No, it looks like we're out of question for now. If you have further questions, I encourage you to stay because we're going to have another session with a discussion with Professor Huang. At this moment, I want to thank all of you for joining us, and we're going to stop the streaming and the recording.